In section 9.2, we look at different measurements of the concentration of a solution. So an important characteristic of a solution is its concentration. The concentration is the amount of solute per unit of solution. And a good example of why this is such an important characteristic is to consider these two different solutions of hydrogen peroxide. This first solution is 3% hydrogen peroxide. It's commonly used as a mouthwash and to clean up minor wounds. This second solution here is a 35% solution of hydrogen peroxide. This would be extremely unpleasant to put in your mouth or onto a wound. It would cause a great deal of pain. So hopefully you can see that the identity of the solute is important, but also important is its concentration. Most commonly in chemistry, we'll express concentration in terms of molarity, which is the moles of solute per liter of solution. Molarity is normally given the symbol uppercase M or moles per liter. To calculate the molarity, we take the moles of solute and we divide it by the volume of solution. So typically in problems, we'll be given the amount of our solute and we might have to do some conversions to get it to moles. For example, we might be given the amount of solute in grams and we'll have to turn that into moles. Similarly, we'll be given the volume of our solution, but it might not be in liters. So for example, it might be in milliliters and we have to convert that into liters before we can perform the calculation of molarity. So a good example of that is this problem here. It says, what is the molarity of a solution formed when half a gram of sodium chloride is dissolved in water to make half a liter of solution? So we're lucky because our volume is given in liters, but our mass of solute or our amount of solute is given as a mass, not in moles. So the first thing I'm going to need to do is to take my half a gram of solute, multiply it by 1 over the molar mass, and then turn that into moles. Now I can go ahead and calculate my molarity by dividing the moles by the volume in liters. So 8.5 by 10 to the minus 3 moles divided by 0.5 liters, and here's my molarity. A common calculation that you'll be asked to perform is to calculate the mass of solute required to prepare a given solution. Now the nice thing about this is we can demonstrate that you can come up with a pretty simple formula for doing this in one step every time. So here's a good example of that. It says what mass of sodium chloride is required to prepare 100 milliliters of a 0.5 mole per liter solution. So we know that molarity is equal to the number of moles divided by the volume. Or reorganizing, we can say that our number of moles is equal to the molarity times by the volume. You may also recall that number of moles is simply equal to the mass over the molar mass. So what I'm going to do is I'm going to put mass over molar mass in place of moles in my top formula there. So that leaves me to here. Mass over molar mass is equal to the molarity times by the volume. Now I'm going to multiply both sides by the molar mass, and that leads me to this formula here, which says that the mass of solute is equal to the molarity times by the volume times by the molar mass. So my molarity is 0.5 moles per liter. My volume, because I have 100 milliliters, that's the same as 0.1 liters. So there we go, molarity times volume gives me moles. And then finally, we're going to multiply by the molar mass, 58.44 grams of sodium chloride for every 1 mole of sodium chloride. And you can see moles cancels out and it leaves me with grams. So I would need to weigh out 2.9 grams of sodium chloride to make this solution. So just recapping, the mass of solute is simply equal to the molarity times the volume times the molar mass. You multiply those three numbers together and you solve the problem. Another classic problem when working with concentrations is a dilution problem. So in a dilution, what you do is you begin with a concentrated solution. We often call this solution number 1, or sometimes people will call it the stock solution. We'll take a small portion of it. So in this case, we took half of it, and then we'll add some solvent. And in this case, we added 500 mils of solvent. This is give us solution 2, what sometimes we call our dilute solution. So we move from our stock solution to our dilute solution. Now, an important observation to make is that the number of moles that we took from our stock solution is exactly equal to the number of moles that we end up with in our dilute solution. So the number of moles is equal to the molarity times by the volume. We can prove that because molarity is moles over liters. If we times that by the volume in liters, you can see we get moles. And the number of moles that we take from the stock, in this case we took 3, is always equal to the number of moles that we end up with in our dilute solution. Another way of saying that is the molarity of the stock times by the volume we took from the stock is equal to the molarity of the dilute solution times by the volume of the dilute solution. And so this little formula here is called the dilution formula. And the nice thing about it is it will work with any volume units or any concentration units, provided they are the same each side of the equals sign. So if V1 and V2 are both in milliliters, you don't have to convert to liters. Okay, so this is an example problem of using the dilution formula. We'll do a couple of these. It says, how would I prepare 25 milliliters of 0.1 molar solution by dilution of 2.5 mole per liter stock solution? So we're going to begin with our dilution formula, and what we know is the concentration that we're starting with is 2.5 moles per liter. The concentration that we're ending with is 0.1 moles per liter. The volume that we're ending with is 25 milliliters, but what we don't know is how much of the stock, how much of solution 1 do we need to take to dilute down to the 25 milliliters. So what we're going to do is we're going to take the dilution formula and we're going to reorganize to solve for what we're trying to find out, V1 in this case. So to do that, I've divided both sides by C1. And now I just put my numbers in. So we have C2, which is 0.1, multiplied by V2, which is 25, divided by C1, which is 2.5. And you can see that moles per liters cancel out, and it leaves me with milliliters. And when I put this in the calculator, it tells me that I need to take 1 ml of the stock solution, and then I would have to add enough solvent to get this up to 25 milliliters. So you can see I didn't need to do any conversion of my volume unit into liters, but the units have to be consistent all the way through. So all volumes have to be in milliliters and all concentrations need to be in molarities in this case. Here's another one, just so you can see how it works. It says, how would I prepare 50 milliliters of 1 mole per liter solution? So V2 is 50 milliliters and C2 is 1 mole per liter. That's what we're trying to make. C1 is 5 moles per liter and V1 is not given. We don't know how many milliliters that is. So we're going to take the dilution formula. We're going to divide both sides by C1 so that we have an expression for V1, and then we're going to put our numbers in. So C2 was 1 mole per liter, V2 was 50 milliliters, and C1 was 5 moles per liter, and we can see that moles per liters cancels out, leaving milliliters, and when we put that into the calculator, we get 10 milliliters. So what do we need to do? We have to take 10 mils of the stock solution, solution 1, and then we're going to add solvent until we get up to 50 milliliters, and then we will have solution 2, our diluted solution. Okay. So while molarity is a very common measure of concentration in the chemistry lab, sometimes it's too concentrated to be practical. So in many applications, in particular in healthcare and in environmental science, it's better to express concentration in units of what we call parts of solute by parts of solvent in terms of mass. So when we have dilute solutions, it's very common to express concentration in terms of milligrams of solute per kilogram of solution. And that's a bit of a mouthful to say, but as there's a million milligrams in a kilogram, this is often described as being parts per million, or abbreviated even further as ppm. So we can see here, this is some data from NOAA, and we're looking at concentration of carbon dioxide in the atmosphere. It's not very much, and so they've expressed it as parts per million. So when we see a number like 400 parts per million, we can rewrite that, if we want, as 400 milligrams of solute for every 1 kilogram of solution, because that's what it really means. Now, if things are very, very dilute, and a good example of this would be stuff like hormones, which are present in tiny, tiny little amounts, we might work in micrograms of solute per kilogram of solution. Now, it's worth noting that in 1 kilogram, there are 1 billion micrograms. And so for this reason, this particular unit is often referred to as parts per billion, or ppb. So you can see here, these folks are measuring the concentration of copper ions. Copper ions are an antibacterial, and they're quite active at low amounts. And they're measuring from a few tens of ppb copper up to a few hundreds ppb copper. So when we see a number like 500 ppb, you can think of that as meaning 500 micrograms of solute per 1 kilogram of the solution. Okay, so we've had 3 different measures of concentration so far. We've had molarity, ppm, and ppb. In many applications, and this often comes up in healthcare, concentrations are expressed as percentages. And we saw an example of that when we were looking at the hydrogen peroxide solutions. We have to be a little bit careful with percentages, because we might be given a percent by mass, and we might be given a percent by volume, and generally these things are not equal. So when we write our percent sign, we always want to label it as whether it's mass over mass or volume over volume to make it clear to the reader what is going on. So if I want to calculate the concentration of solution in percent by mass, what I have to do is take the mass of solute, divide by the mass of the solution, and times by 100. Now there's only one thing to be mindful of, is that the solution includes both the solute and the solvent, so you might have to add the masses of two things together in order to get the mass of the solution. We can also calculate the percent concentration of a solution by volume, and it's done similarly. To calculate percent by volume, we take the volume of the solute, divide that by the volume of the solution, and times by 100. This is a little bit easier because we don't normally need to add together a couple of numbers to get the volume of the solution. So this says, what is the percent by volume of 125 mils of an aqueous solution that contains 47 milliliters of ethyl alcohol? So the volume of the solute in this case is 47 milliliters. So we've got that. The volume of the solution is 125 milliliters. So we've got that. So now we just put it into our little formula, and we make sure that after our percent sign, we put the volume on volume indicator to show that this was a percentage calculated using volumes and not mass. Here's an example of calculating a percent by mass concentration. So it says, what is the concentration, what is percent by mass of a solution composed of 7.6 grams of sucrose dissolved in 83.4 grams of water? So this is the minor component, so it's the solute, and the water is the major component, so it's the solvent. So to calculate the percent by mass, we take the mass of the solute and divide it by the mass of the solution. And you can see a little bit more work here because we have to add together the masses of the solute and the solvent. Make sure you put this in parentheses when you put it into your calculator. We do that, times it by 100, and when we give our answer, remember to add the mass on mass indicator after the percent sign, so people know that this was a percentage calculated using masses and not volumes. So why do people like these? Well, they're really commonly used in healthcare because they can make simple dosing calculations a little bit easier. So when a solution is labeled as 15% mass on mass, how people are going to interpret that is that you get 15 grams of what you're interested in for every 100 grams of solution. So if I wanted to give a patient 30 grams of the solute, I know I'd have to give them 200 grams of solution. When it comes time to using these concentrations to do calculations, we're probably going to use them as one of these two conversion factors. I'm going to use a conversion factor that expresses that I get 15 grams of solute for every 100 gram of solution, or alternatively, that 100 gram of solution is equivalent to 15 grams of solute. Percent by volume is used similarly. If I was told that I had a solution that was 6% by volume, I would interpret that as meaning that I got 6 mils of what I'm interested in for every 100 ml of solution. So if I wanted to give a patient 18 milliliters of a particular substance, I'd go, well, 18 is 3 times 6, so I'd have to give them 300 milliliters of the solution. If I needed to do math, I would probably use that concentration in the form of one of these two conversion factors. The 6% volume on volume can be interpreted as meaning you get 6 mils of solute for every 100 ml of solution, or alternatively, for every 100 ml of solution, you get 6 mils of solute. So people like these types of concentrations because it avoids the use of moles. Okay, and that concludes the video for section 9.2.